My name's Jeff. I'm with the Edge of Space Sciences as of maybe a couple of years back. One of the things we want to talk about this morning is some of the software-defined radio stuff we've been using with APRS to track balloons. It has been an adventure, I will say that. A little bit about Edge of Space, Denver-based. Primary mission is, of course, promoting science and education through high-altitude ballooning and some amateur radio. They've had a lot of history with this group. I am probably one of the newer members, as the guys were just ribbing me. 289 launches. Hopefully tomorrow will be 290. And one of the challenges with this group is all the payloads that have to get flown around. So a lot of times, and it's not uncommon to have 4 balloon flights in a day, and each one with multiple APRS trackers. That makes it a little bit challenging trying to figure out what's flying around and where's it going and logistics of who's supposed to go get it. In addition, there's new technologies coming around, things such as ADS-B, radiosonde data that we're thinking about trying to consume, and of course, more customers always makes that a little bit more challenging because we have more people wanting to do more payloads, more size, more flights. So what are we building? We decided to build some sort of a system, and I've got a demo here I'll show you in a second, that would help us keep track of all of these flights and all these APRS beacons running around and make logistics and recovery a little bit easier. So we were talking about what is a tracker, because we decided to call this an SDR-based tracker. So the first thing you think of with a tracker is, well, we think about one of these small little transmitters, one of these little beacons. And then during one of the initial build conversations, I was talking to Nick Hinks, one of our more tenured members. He's like, Jeff, no. A tracker is not a thing. A tracker is a person. I'm like, okay, a tracker's a person. So my mind immediately went to Terry Grant and man tracker. I'm like, okay, right, man tracker. And I thought, okay, wait a minute. Maybe Nick means something else. Maybe he means the poor late park ranger for Jurassic Park who was not a tracker but was probably a trackee. So then I thought, well, okay, we're not talking about any of these things. We're actually talking about a system which involves radio, bit of hardware, bit of software, and of course an antenna to track balloons. So we're talking about that system of stuff, and so we decided, that's what we're going to call the SDR tracker. So with that said, what is this little contrivance? It's essentially an application that we run on a specialized piece of hardware similar to this, which is just a small computer that aids us in payload recoveries. It's software-based, so we don't have any traditional radios. We're not bound by some of the limitations of that. And because of that, that gives us some advantages in being able to listen to multiple frequencies and process packets off of each of those simultaneously. The EOSS tracker? The brick. Yeah, so it's affectionately dubbed the brick. So add in a couple of features that allow for offline use, such as offline maps from OpenStreetMap and a little landing prediction, and you access it via a web browser. So it's very lightweight. We don't have a thick application, a heavy application you have to be running. You can run on your laptop. I guess that would be heavy. But common thing to do is to use your phone or your tablet to get access to it. Oops. I'm going backwards. There we go. It's receive only out of the box. Nothing's transmitted anywhere, so you can have non-hams use it. You don't have to be a ham to use it. And nothing is uploaded to the internet. Double star asterisk there because there are some features that you can enable. If you're a ham, you can iGate, and if we have an external radio connection, you can, of course, beacon over RF. So the basic idea starts with the brick, which is a small computer, a little industrial one, which we've picked, and we can talk about this being sort of a software-only solution later. This gets deployed in folks in their vehicles, at the ground station, and the idea is you pick something, and you can see the little Wi-Fi antennas off of this. You pick something that has Wi-Fi capability that can start up its own personal little local Wi-Fi network. couple that with the small little SDR USB dongle, which is very popular. I think you can get these for as low as $23 now or even less. A 2-meter antenna, a little software, and then we can connect to this Wi-Fi network via our tablet or our phone and then interact with the device, no wires, device of your choice. So how do we connect this in the vehicle or at home? If you're at home, of course, you need a 12-volt power supply. That's one of the reasons we picked this device. You might have the need for DC to DC shenanigans, depending on what sort of vehicle power you're putzing with. Of course, you connect your stick up via USB, connect that to your antenna, connect up a USB GPS, hit the power button, and presto, you have a Wi-Fi network that pops up, which then you grab your device and you log onto that. Whether that's your laptop or tablet, or in Jeff's case, he's got a fancy G-Tac there. But once you have connection to the Wi-Fi network, you're off to EOSS tracker.local in your web browser. And now, keep in mind, this is all offline. This isn't internet connected. This isn't plugged into a network somewhere. And once you're on that page, then you get to the home screen. So the next few slides just sort of run through kind of a flavor of what the interface looks like. And then we can get under the covers and look at the guts as to what pieces of open source software we're leveraging, how things sort of work, the sausage making, if you will. So in the left-hand corner, we've got current status. You can see what frequencies the system is listening on. It's of course green, so that's good. You can look at processes in the middle. Things that are running. Green is, of course, always good. You can start and stop things. And, of course, on the right-hand side, you can see, well, what's the GPS puck listening to? Does it have one satellite or 3D fix or nothing? So that's the home screen. One of the first things you want to do with the system is set it up to track your balloon flight. And in that case, there's the setup screen, which, of course, lets you do several things. Try to run through this relatively quickly because this is a little bit boring. But in any event, the first order of the day is to set up your flight. And so that's some sort of identifier, either call signs for the beacons that you have on your flight string, what frequencies they're going to be transmitting on, and if you have trackers, and we're mixing the word up again, if we have trackers out in the field that are beaconing their position from their vehicle, what are their call signs, what's their name. A lot of times with EOSS, I can't remember what everyone's call sign is and the name associated with it. So I'm like, hey, Joe Bob, I need to, oh wait, that's tracker somewhere. So you can keep track of that. There's prediction data. Now we have the luxury, we have Randy that does our own pre-flight predictions from a weather perspective, but we're looking towards trying to make it much more generic, so we have CSV data that can be ingested, so on and so forth. There's launch sites, like Pella being one of them. You can put in your lat long and elevation. And of course, there's a list of frequencies and system configuration. So to set up your flight, just stick in a name and identifier in here. We have EOSS. They have a convention that we like to follow as far as the name description, the drop down for what your launch site, where that's going to be. That helps with landing predictions. And of course, do you want to track this on the map? So all of this happens in a GUI, so you don't have to worry about command line stuff or bringing up APRS.fi. This is all sort of self-contained. And then you got chances to list and add your individual APRS beacons on your flights. So this is where the drop-down box, you select which, or drop-down menu, select which frequency you want that call sign to be on, or it's transmitting on. Hopefully you know that. For EOSS, there's a select set of frequencies that the crew uses to pick from, so that's just a note that they have that, but you can assert, were you to install this on your box, so to speak, you would be able to enter those frequencies later. So trackers, unlike Terry Grant, the man tracker, or the game warden for Jurassic Park, we can enter folks here. Now there's this concept of teams. We've define teams as the phonetic alphabet, so there's the Alpha team, the Bravo team, Charlie team, so on and so forth. And individual folks, such as in 6BA myself, as you can see here, would be plugged into one of those teams. And from that, in this example, we're just adding Jeff as the tracker, and we're going to add him to the golf team. And once you've added added folks to a team. You can see here's the golf team. There's 2 members in here. Unfortunately, I got teamed up with Marty on our team. Sorry, Marty. And we're all on the golf team. We demoted you, Marty. You're normally an alpha, but we demoted you. So. You, of course, can select which flight you might want to assign this person to. So all this has to do with when we get to the map in a minute, you'll see where this makes sense. Each team can be a layer and can be assigned to a flight, and they'll show up as a layer that's toggleable on the map. So you don't have to list everything on the map. You can display the things that are most relevant to you. So you can change which flight we're assigned to. Maybe we're at large. And of course, you can change which team an individual person is. You can just flick them around and move them to another team. The point of which is so that when you're on the map, you can see this is an APRS beacon from golf. So one of these call signs was beaconing that, and they show up on the map as the name of golf. So you can set up your frequencies. Of course, the unit will always listen on .39. That's, of course, something we'll probably change in the future to make it a little bit more universal. You just pop in a new frequency, and it shows up in the list, and then it's in the drop-down list so you can assign it to flight. There's launch sites. Plug in things like the launch site for GPSL. Mike gave us coordinates, and I don't know if that elevation is right or not, but plug that in. A lot of these are EOSS specific launch sites, so the team, when they want to add a flight and they're using their brick, they just have to select from that drop-down. There's system configuration stuff like time zones. So I think, where's John at from Texas? So he's, of course, in a different time zone than most folks that are in Colorado. No problem. He can just flip the switch here and move to Tahiti time zone or wherever he happens to be, and all the times are reflected and it's updated. You can, and I mentioned, if you are a ham, of course, you can enter things like your call sign, SSID. Do you want to iGate from this brick? So you might have 6 different frequencies this is listening to. So any APRS packet that comes in on one of those frequencies, you could iGate it, assuming you plug the brick into the internet somehow. Of course, so you got a chance to enter that. You can add your comment and symbol. Also, if you're a ham, you can hook it up to an external radio. A lot of times this happens over a USB connection. You have a drop-down box here. It can detect what is in there. And of course, usual parameters such as how often do you want to beacon? You want to beacon every minute, every second, every 10 minutes, whatever that might be. And this comes with a big giant caveat because to date we only have 2 of us that are actually using it in this manner. So we just haven't had enough exposure in the wild to say, hey, this is rock solid or not. So this is still early stages of getting that to work. But early results are promising. In fact, I've been running it in the truck this whole time for the past all of 2019 in this manner. So it beacons basically from the brick. I don't need to do that from my truck radio. There's data that you can look at. So there's a list of live packets that are coming in. Now these update every few seconds on the screen, so it's not instantaneous. So you can look at all the actual text packets that come in. Now whether they come in over the internet, because there are network ports on the back of this, so you could plug this into your home network or your home Wi-Fi, so for example, or if you have a hotspot in your truck or vehicle. And in the graph, well, the colors didn't come out so good in that, but the orange is the RF thing, packets that came in over RF, meaning came in over the SDR stick. And then of course blue are packets that originated from the internet, and that means someone else iGated the packet for you. You just happen to pick it up. And finally, we come to the map. So this is the OpenStreetMap map tiles that come in here. You'll notice on the left is a sidebar that folks can get access to operational information. And up in the right-hand corner is the list of layers that you can toggle on and off. You can pan and zoom and mouse around all you want. It's very tablet, very phone friendly. For EOSS and this brick specifically, we've pre-rendered a lot of the tiles, and they're on there so you don't have to worry about, as you zoom in, have to have the tile be generated. Now, we'll generate a tile automatically for you. It just takes a little time to do that, a few seconds to do that. But for EOSS specifically, and most of, as you can see here, eastern Colorado, all of those have been pre-rendered. It updates every few seconds, so you get an update of what's in the field. Any new packets come in, they get plotted on there as an object. Very similar to APRS.fi in that manner, so you can just mouse around, click on an object if you want, or toggle that layer off altogether. So, as I mentioned, there's a little sidebar on the left-hand side. You can click one of those icons and pop it out. In this case, we're looking at flight EOSS 999, which of course doesn't exist. But there's some flight gauges here that will update with the latest information from any beacon on that flight. So if this flight is at 10,000 feet or 100,000 feet, you've got sort of the aircraft dials here. We've got, current altitude, vertical rate, heading, and speed, essentially. So you can toggle through some of that. There's a bunch of other things below the dials as far as data for the flight specifically. So on one flight this year we had, was it 6 or 7 beacons, I think? And all of those are displayable as far as like position packets and stuff like that individually. You can toggle layers on and off. Most folks spend their time on the map, especially if you're out trying to hunt something down. So here's an example. This was a flight early in the year. This is actually 2 flights. Now on each flight, AE0SS-13, for example, there's actually 2 APRS, I'm going to say it, APRS trackers, APRS beacons on that flight. And of course, AE0SS-12, there's a couple of beacons on that flight. In this case, we're looking at flight 287, and you'll see here, of course, it'll plot the actual position of those on the map, which is similar to what you see with APRS.fi, except in this case, it's a little bit more specialized and purpose-built for that. There's, of course, a predicted flight path. Now, that's the pre-launch weather-based flight path that we're predicting, and sometimes that's 12 hours old. But you can plot that as an overlay on the map, so you can kind of see, well, which direction should I go drive when I get out on the field. There's, of course, the flight gauges, which update in near real time for each particular flight. So in this case, there's a couple of beacons on this flight, and the latest beacon is displayed. The latest data is displayed. In this case, we're flying around at 77,000 feet. There's the 5 most recent position packets that pops up. So you can tell that there's, I don't know if you can see from here, but there's a couple of different call signs intermixed in here. So that's the 2 different beacons on that particular flight. And you can take a quick glance at the last 10 packets. Where did they come from? Did they come from the internet? Because maybe you had your phone hotspot plugged into the device and it's connected to the internet. Or did they come over RF and over your little SDR stick or your rooftop antenna or housetop antenna? So what happens when it starts to fall to the ground? So that's post-burst or post-cutdown. There's a couple of other gauges on the little left-hand side. There's relative position. And the most important thing you'll see is sort of X marks the spot shows up as the predicted landing location. Now we're only looking at one flight here, but those are plotted for each beacon on the flight string. So you may have multiple APRS beacons on the flight string. You'll get at the moment, you'll get an X marks a spot for each one of them. Of course, you can see trackers are running around out here. Hopefully that's not the Jurassic Park problem. But Golf and Bravo are out in the field here somewhere, beaconing their position. There's the relative location of the flight. In this case, you can see it's 20 miles away, but there's our personal heading is the white and is on the top. So our heading is 237 degrees, but our relative bearing to the balloon or to the parachute as it's falling down, check, falling down is 62 degrees odd, and then the elevation we need to look up is 38 degrees. So we know if we're driving this way or whatever, we need to point this way and look that direction. In this case, it's 20 miles out. We'll probably never see it, but latest packets, status packets as well, and some of the payloads on the APRS beacons. We have that. I think Mark does some of this. There's specialized firmware in there, so it spits out customized messages from a status perspective, so you can see that. So with that said, there's a lot going on there, and as you can imagine, there's a many permutations we could and would probably have to account for, which is why we tried to standardize on some of the hardware. We standardized, of course, on that one little USB stick, which isn't much bigger than this laser pointer. One that's relatively inexpensive, and it's widely adopted and lots of open source software support. We standardized on a small industrial computer. This was an i5. We did test this out ahead of time to try to get something that would hopefully accommodate at least a half a dozen APRS packets half a dozen frequencies at once. And we just picked a cheaper GPS puck. But selecting that set of hardware obviously eliminates a lot of the permutations that we have to accommodate in the field. It's relatively expensive, and as you can see, there's lots of expansion ports on this thing, so if we come up with some new ideas and new uses in the future, then you got somewhere to plug it in. Adopted a GNU GPL 3.0 distribution model. Almost have to do that since a lot of the bricks that this is built on, that's probably a poor choice of words, a lot of the foundation that this is built on is already open source. And picking an Ubuntu distribution just allows us some flexibility. That's a very popular distribution. And in the EOSS ecosystem, as far as the flight systems that are used, some of the team members have already picked and vetted out a number of separate frequencies. So they have a set of frequencies that are designed to reduce interference when we have these multiple flight weekends. And that's one help for that. So that's another standard. Don't have to worry about fat fingering it when you're trying to enter it. I just select it from the drop-down box. So what's under the covers? Well, the core idea is really the separation of concerns between front end and back end. While the back end can be listening to lots of different frequencies, potentially ingesting lots of different packets, depending on how fast of hardware you want to run it on is how fast it will go. While all that's happening, we can be on the front side, mousing around, clicking on things, of course, breaking things if we're so inclined, having our tablets go offline or our laptops crash. All of that can happen without having to interfere with stuff happening on the backside. And all that's because we have a sort of intermediary in the middle. We save all these packets, at least packets of interest, to a database, and it prevents any sort of linkages from front side to back side. So the leg bone connected to the knee bone, connected to the foot bone sort of thing here. We have to start out with, of course, a 2-meter antenna and the SDR stick itself. Some of the small ones are limited to about 2 odd megahertz of spectrum width that you can look at. There's a hardware AGC, automatic gain control on a number of them, but picking this one lets us use a piece of software called GnuRadio, which has widely adopted support for those sticks and can interface directly with them. With GnuRadio, we define the normal things you'd have in a radio, albeit maybe a little bit less, maybe a little bit more crudely, but it seems to work really, really well from our experience in the field. Just channelize stuff, a little low-pass filter, FM demodulation, and out pops downsampled audio, which we hand off to another set of open source software called Direwolf. You're probably familiar with this. It can do a lot of things, such as digipeating. It can do DTMF tones, eye-gating, and things like that. We're really using it to just demodulate these packets. So we want to hand the audio off to Direwolf and have it spit out an ASCII text packet, which we hand off to yet another piece of open source software called APRSc. You might be familiar with that. That piece of software helps run the APRS IS backbone of systems out there. So when you eye-gate something, you're probably talking to a server running out in the cloud somewhere that's likely running APRSc, or the other variant of it, which is, I think, a Java-based application. So all of this is running on the brick. So nothing is running on your tablet or your laptop. This is all running on the back-end computer. Of course, Aprsc, if you plug this back-end computer into a network and connect it to the internet, then of course it can talk to some of the APRS servers up there, and APRSc servers up there in the cloud, and that you can potentially assuming you do this, potentially have packets ingested into the system over the network. So it doesn't necessarily have to follow this horizontal sort of path in. APRC, of course, is things that you can connect other APRS clients to, such the gold standard currently for EOSS is EOS TrackPoint, which Nick I think is the author, and that's been widely used in the field, works very well. Or you can connect other APRS clients to this, like APRS ISCE, Yak, Zaster, or your own Python. And in this case, we have sort of what I've dubbed the vampire tap, which we plug into it, and that's the mechanism with a little bit of filtering where we save packets into a database. Add to that some OpenStreetMap goodness, a little Apache web server, stir really well, and you end up with something that we can connect to it from our tablets or our phones and interact with it. So obviously, we're talking to a web server. When we bring up the web browser on our device, we're interacting with, in this case, this is an iPhone. Someone is texting me, an iPhone with Safari. So we would interact with our web browser on our tablet, and then that, of course, interacts with the web server running on LayBrick. But running on the brick is essentially a back-end piece of Python code that sort of coordinates all of this. Its responsibility is to launch, of course, when one hits the start button, this is what happens. It'll launch GnuRadio processes which talk to the SDR dongle and listen to the 2-meter hand band for APRS packets on whatever frequency we've told it to listen on. It'll also start up Direwolf. It'll start up APRC. It'll start up the vampire tap that I was mentioning before that tries to grab packets and stuff them into the database. It'll listen to the GPS, and it'll also, or start the GPS, it'll also start up the landing predictions function, and all of that sort of happens, so you don't have to interact with it. Data, of course, flows, in this case, APRS packets or audio, in this case, from GnuRadio to Direwolf, processes packets, sends it to APRC, and the vampire tap grabs those and, of course, stuffs them in the database for use by you and I later through the web browser. So what does a single processing chain look like from GnuRadio? So there's some things missing here. But I guess for the ability to view it on the screen here. On the left-hand side is the source, and that's the interface to the USB SDR dongle. You tell it things like frequency you want to be on and sample rates and things like that. Pass that off to something that can create a channel, a low-pass filter. So this is sort of digital signal processing smarts that would go into this. Small narrowband FM receiver, convert and scale the audio output, and then we have a UDP block to send that audio over a network connection to Direwolf. Now all this is happening on the brick. There isn't anything leaving the brick. And because you can read that so well, have a big version of this. So of course this is the source. Now on this you defined some of this happens all automatically, and this is the graphical interface to GnuRadio called GnuRadio Companion. So this is the thing where you can, with your mouse, you can drag and drop these blocks around on the screen and connect the dots and connect lines and things like that. Little audio interference there, yes. So in any event, this is very graphical, but on the system itself, it's all Python. It does all this automatically. There isn't any sort of graphical component to the GnuRadio portion of that. So you're insulated from all of that on the covers. So you define things like turning on the gain mode to automatic because we want to use the AGC on the little USB stick. Our center frequency, in this case, we just sort of plugged it in as 145, and sample rates are all determined automatically. All of that information is then handed off to the frequency translating FIR filter. All of those parameters are generally determined programmatically and automatically. The low-pass filter taps, check. Low-pass filter taps, of course, defined there. And then how do we figure out that we should be having a cutoff frequency of 5.5 kilohertz? The little reference over here, which you may not be able to read, it's just Carson's bandwidth rule. 98% of the power is within, a couple of kilohertz there in this case, out from center. And of course, because we couldn't fit all on the screen, all that hands off to the narrowband FM receiver, which we tried to match up the max deviation with what a lot of the payload packets are, or the APRS beaconing packets on the flights are using. So we're trying to marry this up to participate nicely in the flight systems ecosystem that we have. Scaling the audio, and then of course the UDP block to send that over the local host. Find the button. The local host address to Direwolf. And again, all that's happening on the brick. Okay, so that's great, but what about if you want to do this a bunch? So we want to listen to a lot of frequencies. You might want to listen to 9 different frequencies at once, which you could do. And if you were to make a nice little GUI out of this, you would have a lot of blocks on your screen. And it would be really tiny like this, and you wouldn't be able to read it. So we do that on the brick, except we don't have the graphical component of that. The one thing I would caution you of is that in this case, those little USB sticks can only do about 2 megahertz or so spectrum width they can look at, which is one of the reasons we centered on 145 megahertz, because then that means you can listen to anything between 144 and 146. All this happens in parallel. There isn't any sort of serialness to it, which is one of the benefits of the SDR. This is, of course, dependent upon how much juice you have, CPU power primarily, in the computing device you want to run this on. You could have probably run 20 frequencies if you wanted to, but we'll need something much bigger than the little brick to do that. And of course, we have it automatically. One of these frequencies, typically the first one, is always set up to listen on .39. So what happens with all of that when we get over to Direwolf? Well, with Direwolf, you can't see that actually. So with Direwolf, you set up a configuration file, which is just a bunch of text, and you have to give it things like, well, what's the network port you want it to listen on? There you can see UDP 1200, which comes from GnuRadio. You have to enter stuff like your call sign in this case. I've got mine in there, what sort of audio sample rate you have, so on and so forth. And you have to find how many of these quote, quote, channels you want to listen on. So that GnuRadio, we'll marry that up with what it's listening on, and maybe channel 1 audio goes to this config, channel 2 audio because of that, channel 3 goes to that. Now these would be 3 separate frequencies. Perhaps this is .39, .34, .36, for example, and we're listening to all 3 of those. We're telling Direwolf, hey, this is what you're supposed to do with that, and listen for packets coming in on any of those. All of those, of course, get handed off. We tell Direwolf this. That's at the bottom of the config off the screen here that you can't see. We tell Direwolf to send that to APRSC. And at that point, there's another text config file you have to muck with. In this case, there's things like server ID or passcode, email address, so on and so forth. All of this gets done automatically for you by the brick when you hit the start button. You don't have to do any of the config files. Of course, yep.
Does the machine look at those frequencies in a serial fashion?
The question was, does the machine look at those frequencies in a serial fashion, decode packets off the first one, when it's done, decode packets off the next one when it's done, and then maybe round robin back and start again? So the answer is no. It does that all simultaneously. They're all parallel execution threads. Now granted, ultimately, right, it's getting time sliced on a CPU, but this is like multi-gigahertz stuff, so it happens really quick. Yeah, go ahead.
Is that why you're using GnuRadio instead of like Aprsc?
Yes, so in fact, with GnuRadio, since there's a lot of programming APIs, so the question was, is that why we're using GnuRadio instead of maybe RTL FM? And the reason is we can programmatically specify exactly what we want from a frequency for that, and then have control over the whole process with the API. There's a Python API. There's, I think, also C API that we can interface with. So that's primarily the reason we chose that.
The other reason, if you put multiple frequencies in the RTL FM and scan that list, it's sequential. It doesn't do those correctly.
Yeah, Jeff's comment was, for those online, was that RTLFM will scan those frequencies. It doesn't do it in parallel. So,
You might point out that Direwolf does need a tweak for the multiple channels coming in.
yes.
Out of the box, it doesn't do that.
Yep. So let me go.
Already it's limited to 2 or 3 channels.
Yeah, by default, Direwolf out of the box, unless you compile it yourself and make a change to the source, will only be set up to listen to 3 channels, because who would be dumb enough to want to listen to 6 or anything like that at once? But
Got a
Yep.
question online. How many SDR dongles, considering the limited band, how many dongles can you support?
at the moment, we've used up to 2, and part of that is just we run out of USB ports. But the second reason is, I guess I should restate that. Sorry, the question was, how many SDR dongles can we run at once and potentially support? Was that the question?
Yeah, I believe so.
Yep. So at the moment, we can support up to 2 automatically, and it'll try to listen on the same frequencies on each one. Now that's kind of redundant, and it is. But at the moment, we're still discussing what to do with that. There may be some ideas where we could do ADS-B, for example, on one SDR stick, and maybe do regular 2-meter handband or APRS on the other USB stick. And then there's actually thoughts about what if we had 3? Well, maybe we could do something like grab radio sound data from the third one and maybe ingest that and save that to the database, and then be able to provide more accurate predictions for where the flight's going to go that morning, or flights, plural. So I guess at the moment, the answer to the question is we can support as many as you can, assuming you have USB ports and a computing platform that will accommodate it. But really 2 is the answer at the moment. And in fact, it's really just 1, because if you plug in 2, that means, of course, you need to have 2 USB sticks, and you need 2 antennas. So it's multiple stuff. But oh boy, okay. 2-minute warning. Yes. Well, we're almost done. So APRSC, one of its strengths is it can ingest packets from a variety of sources, whether you're connected to the internet or over the radio and the SDR. One of its primary strengths is it can eliminate duplicate packets. So in the case of multiple SDR sticks, we might get the same packet twice. It doesn't matter. It all ends up landing in APRSC's lap and tosses out the redundant ones, and we end up with 1 left over, which can get sent to external clients if those are connected to the brick, or in our case, the Vampire tap that we're using to send those packets to the database. I'm going to skip a little bit of this, but we use separate call signs depending if you're a ham or not. If you're a ham, your call sign gets tossed in here. If you're not, we use something else, and it's all read-only. We do landing predictions, so the best case that can happen for you is you hear packets as your balloon is ascending, and those get saved to the database. So we grab those wind vectors, north, south, east, west type stuff, horizontal, and save those. So if we don't hear packets, we don't get packets, then you're making averages later on. Yep.
Do you have to have a predict file loaded to get predictions?
No, you do not have to have a predict file loaded. So you may, and this happens frequently, you may not hear the first packet if you're downrange until the flight gets to 10, 12, 15,000 feet. So obviously you're making an average from the point that it launched to this first packet that you heard. So the more packets you hear, the better off you are, of course. We make some compromises with up, down, downdraft, or updraft, downdraft, wind, just try to do a mean average. It doesn't, I think that's a bit of a losing battle, but it's the best we can come up with at the moment. So if you were to plot the descent on a graph, and the top right-hand corner, that would be the descent velocity, to say, on the graph, altitude on the bottom, velocity on the vertical axis. The top right-hand corner is where the balloon burst, and it starts to fall. So, of course, your altitude is 100,000 feet, or whatever that might be, and your velocity is relatively high. So, of course, when the thing is landing, it's the opposite. Your altitude is, of course, low, and your velocity is low. So we try to split that up, because at the beginning of the flight, you just don't have any data to base any notion of what sort of drag coefficients the parachute's going to have, how heavy it was. Try to limit this so that folks don't have to enter things Like, well, how big of a parachute are you using, and how heavy was all the payloads, and one fell off because we ejected it off, and so the weight of the whole flight string got reduced halfway through. So folks don't have to enter any of that. But because of that, we do a little bit of curve fitting at the beginning of the flight when we don't have any data points. And as we get more data points as the flight descends, we can estimate, of course, drag coefficients and stuff just based on what we observed, and then ultimately plot that on a map as the X marks the spot stuff happens. So as the flight descends, you'll see these burst things pop up on the map as the approximate burst location, or where the descent point began. And then, of course, shortly thereafter, you'll see the X marks the spots. So what's next in what we have planned? At the moment, we're setting on version 1.1. There were a lot of fix-ups here. We started, of course, with the initial image back in January. We have been talking about, I'm skipping over this quickly, sorry. We've been talking about forking this into two directions. One that's EOSS specific, largely because it's purpose-built for dealing with this little brick. And we already have 30 plus of these things out on the field to support. So that's one side of things. And that little brick has to accommodate something on the order of about 250 gig worth of map data, which is not very easy to download. So because of that, we're thinking we should split this into a community-based version, which would be great. We already have some stuff set up on GitHub. Work is going on to remove some of the EOS-specific stuff in there, like some of the frequencies, and of course the word EOSS seems to be everywhere. Get rid of the offline maps, and that saves you the 200 gigs of download. And this is sort of a homework exercise for the end user, but it can be an easy path into running this on lots of things, not just a brick, like your laptop or your home computer or wherever you want to put it. And we can also track your flight tomorrow. Shameless self-promotion. And thank you. That's it. Yep. Yeah, yeah.
They used to have something made by a company called Global Magic, which was the interface to Visual Basic 6 in the good old days. But I haven't done anything like that until you showed me. Where do you get those dials and how do you interface?
I found some of that, which was open source, and they didn't look like that. So I've actually taken those and tinkered with them. But it's really HTML, CSS, JavaScript type of stuff. So it's not hard graphics, if you will, a hard image. It's actually dynamic.
Okay.
Yeah.
And where could you find the source of those?
I don't remember where I found that originally, but that sort of got me off to the path of, okay, maybe we should use dials like that. And since then, we sort of crafted them from there. But I'll try to find that link. I'll try to find that link.
Yeah, I'd like to at least get started in the right direction.
There's a number of libraries out there that aren't free, they're commercial, and so folks can put that into their flight simulation software or other flight simulator applications. And so I think, and some of those are far more sophisticated than what we had. But when you're driving around, for example, and you're trying to track your balloon, you don't have time to look at some intricate little dial. Just show me where the needle's at, so we kind of ended up with some of that.
Those look great.
Yeah. Yep, go ahead, Nick.
You mentioned the experience that you had in the big SUVs with.
Good point. So one of the experiences we've had in the field is that this has been a boon to being able to track, because we have multiple beacons flying around and lots of flights at times for EOSS. So just in the past, we'd have one radio or two radios, or if you were a really cool guy, you maybe had 6 radios in your truck. But that's really limiting. You can only listen to so many packets at once. But with this, you just have your tablet set up, and you can see all the flights at once. You don't have to see just one, and it's no wires. So we have some CU students that fly with us on a number of occasions, a lot of payloads. So we put one of these bricks in their vehicle, and they had a 15-passenger van with a lot of CU students in the back, which would normally be nodding off as they're driving out in the field to go get their payloads. But in this case, they're all in the back with their phones because they can connect to the little hotspot on the brick and then be able to see everything that our trackers are seeing. They can see where their balloon is at, they can see where their payloads are going to land, and so suddenly they're engaged and excited and they're an active participant, and they're not just along for the ride to sleep because we had a 6 a.m. launch. Yep. It's on the order of 400. Yeah, so it's not, these are not too, you can actually get cheaper models of these or more expensive ones. So it's not, by the time you add in, I think the little USB stick and the GPS puck, we were on the order of about 400. This is from a company called Kansung, K-A-N-S-U-N-G. It's out of China, so I don't know how well you can get those now, but given the tariff situation. But they're fanless, but they do come with a USB fan, which someone has taped this to the top of it because I think they had it jammed in this Pelican box. So, but yeah, it's fanless, runs off of 12 volts.